Let's first examine the functionality of the device. This is receiver coil. Hello, today I will show you how to make a simple wireless power transfer device. I will also perform an analysis of the coefficient of efficiency during transmission of electricity with a relatively high power of 10 and 20 watts. In my previous similar experiment, the focus was on the maximum distance at which usable electricity could be transferred. This time I will try to describe another experiment in which our main goal is to perform wireless energy transfer over shorter distances but with a high utilization coefficient. The device consists of a modified Royer oscillator known as Mazzilli zero voltage switch driver. It consists of 2 or 4 power MOSFETs, transistors mounted on large heatsinks with fans for cooling. Also, a very important part is the capacitive bank composed of several capacitors connected in parallel. In this particular case, there are 6 quality MKP capacitors with a capacity of 1 microfarad each and a voltage of 400 volts. These 2 toroidal coils serve to limit the current. The device is powered by 12 volt power supply from old server computer. Here is the transmitting spool, which is a bifillary wound flat pancake coil. This is the receiving coil, and in combination with this capacitor is a simple resonance circuit. This is a rectifier and voltage stabilizer and is used to drive these LEDs. The frequency of these resonance circuits should be identical to that of the transmitter circuit, for energy transfer losses to be the smallest. On the receiving side are placed loads of 10 and 20 watts, which is in this case a high power LEDs. They are connected to an ampermeter and voltmeter so that we can measure power in real time. Now let's start testing. Now we will measure the losses during the transfer of 10 watts of power exclusively between 2 coils, and we will ignore the losses of the power supply and oscillator circuit. We use this wattmeter for that purpose. First, I will turn on the power supply. Its consumption is about 45 watts. We now turn on the oscillator, and the idle consumption of the whole circuits will be 71 watts. We will calculate the consumption during the transfer by approaching the receiving coil until the diode reaches 10 watts, and we will read how many watts the whole circuit will now consume. The difference between 81 watts and the read results is the losses of the wireless power transfer. Now consumption is exactly 100 watts. Now let's do calculations. Total 100 watts, idle 71 watts, that is 29 watts. LED draw about 12 watts, plus rectifier loses about 1.5 watts. So we spent 29 watts to transfer 13.5 watt at 4 centimeters distance. That is 46.5% coefficient of useful action. That is good result achieved at home. Now let's repeat the same experiment but with 20 watts and smaller distance. The consumption is 124 watts. Distance is 2 centimeters. Let's do calculation again. Total 124 watts, idle 71 watts, that is 53 watts. Let's draw about 25 watts plus rectifier about 3 watts. Total spent 33 watts to transfer 25 watts at 2 centimeters distance. That is 47.1% of coefficient of useful action. These are results obtained at home without precise adjustment of the resonance circuits and are certainly not bad. This is the model that will be used for non-contact charging of electric vehicles in the future. All you have to do is park the car in the garage and the charging will start, very simply. In addition, look at the schematic diagram and how to make the device. This is receiver coil.